Okay, welcome to this video on solving equations containing radicals. We're going to tie this into something that we've learned before when we were solving quadratics that could be written as a binomial square, perfect trinomial binomial squared. Remember when we had quadratics which were this form, like x minus 3 squared equals 4, the way we would undo the square is just by taking the square root of both sides. Right, so we did that, and we said that the square root and the square cancel each other's effects out, leaving x minus 3 because those are inverse operations. And then we had plus or minus, in this case square root of 4, which is 2, and then we finished this by adding a 3, and we got x is 3 plus or minus 2, so two answers, x is 5, and x equals 1, right? Okay, so that solution method, which we learned in the other video, said that we remove the effect of squaring by doing the inverse operation, which is taking a square root. So if we have an equation with a square root in it, like this one, square root of x minus 3 equals 4, we can remove the effect of the square root by squaring both sides. So it's very similar to what we just did. We're just going to square both sides. Remember that whatever you do on one side, you have to do on the other to keep everything balanced. And again, the square root and the square are going to cancel each other's effects out because they're inverse operations. In this case, 4 squared is 16. We only have one answer in this case, which will be x is 19. Okay. We don't have to do the plus or minus because, well, you'll see when we do other examples that we don't have that situation where there's two solutions. Okay, there is one thing that we need to be careful about with square roots though, and that is that we should always check to see whether the solution we calculated is actually a solution for the equation, because very frequently actually with square roots, equations with square roots or radical signs in them, they produce what are called extraneous solutions, solutions which appear to be correct from the algebraic procedure, but when you plug them back in, they're not actually solutions. Okay, so here were the steps that we just did, and we got x is 19 from the previous page there. To check the solution, what you should do is plug it back in to the original equation. So I would plug a 19 in for that x minus 3, and then see if that's equal to 4. So that's going to be this square root of 16 equals 4, so that's 4 equals 4. And so this one does check out, and it means x equals 19 is a solution. But very frequently, we'll get one or two solutions sometimes, and one or both of them are not actually solutions. Okay. So, procedure in general is that if you have a square root in an equation, you isolate that on one side, and then you square both sides to get rid of the square root. So try this one. Let's try this one together. We're going to do the same thing. We're going to square both sides. Let me square both sides. And so the square and the square root will cancel, and I'll have x minus 3, and then negative 4 times another negative 4 is positive 16. And when I add 3, I get x equals 19, the same solution from before. Okay, so I believe that's the solution, but I'm going to check by plugging back in. So here's the equation that I'm substituting into, and I put the 19 in for the x, and I get square root of 16 is negative 4, and I get 4 equals negative 4, but that's not true. That's not true, and that means that this is not the solution. This is what we would call an extraneous solution. Which means, in fact, since we were only able to find one value that might work, and it didn't work, this equation has no solution at all. There is no solution to this. There's no real value that we can plug in for x that will make this equation true. And so we just say there's no solution. So you really do have to check very frequently. Why is it that these kind of equations with square roots have extraneous solutions? Well, it has to do with the shape of the square root curve. If you take that equation and you look at the left-hand side, maybe I could try different values of x and try to attempt to graph the left-hand side and see, well, where does that graph look like it's going to be equal to negative 4? Well, if you plug a 0 in for x, 0 minus 3, that would be taking the square root of negative 3, and so there's no solution to that, right? If I plug a 0 in, there is no solution for the curve, right? If I plug a 1 in, same thing. In fact, I have to go all the way up to x is 3 before I get square root of 3 minus 3, or 0. So the point 3 comma 0 is on the curve right here, right? If I plug 4 in there, I get 1 out, so the point 4 comma 1 is on this curve, right? And so actually, if you start plugging various values of x in, none of the values up until 3 work at all. And then when we do plug values in, we only get positive values. So in fact, there's no place where the left-hand side of this equation will ever equal -4. And the reason why this happens is because of this unusual shape for the square root curve. So equations that contain it very frequently have these extraneous solutions. So you don't have to graph it out every time, but I just want you to know why they occur and that it's really important in this case to check solutions. Okay, we're just going to do a few more examples. If at any point you feel like you've got it, pause it, try it for yourself. For this one, I'll give you a starting hint. You want to go ahead and add 2 to both sides so that you can isolate the square root first before you square both sides. So continue from there and then unpause the video. Okay, so when we do that, let's see, we would square both sides. The square and the square root cancel. 2x plus 4 over here and 4 on this side. And if I subtract 4 from both sides, I get 2x equals 0. And then if I divide by 2, I get x is 0 because 0 over 2 is just 0. So that's what we believe the equation is, the solution is. So let's double check that and see. If I check that, I should plug it back in and see if it works. So I'll put that 0 in for x, anywhere there's an x in the equation. And that would be the square root of 4, because 0 times 2 is 0, so it's 0 plus 4, just 4. That's going to be 2 minus 2, and so actually this one did work, and so this one is a solution. X equals 0 is the one solution to this equation. Okay, what do you do if you have multiple square roots? Well, we're going to be able to isolate one of them. We can't isolate both of them, but we're going to pick the one that's the most complicated looking to isolate, because that way when I remove the square root, we'll uncover the largest or most complicated piece we can. So in this case, 2x plus 1 is a little more complicated than just x, so I'm going to first isolate this one by adding a square root of x to the both sides. So I have square root of 2x plus 1 equals the square root of x plus 1 on this side. Okay, now that I've got that isolated, now I can square both sides, but you got to be really careful. You're not just squaring the square root, you're squaring the entire left side and you're squaring the entire right side. So these cancel on the left side, leaving 2x plus 1. But on the right hand side, you have a square root plus x quantity multiplied by another quantity that's identical, square root of x plus 1. So we're going to have to do distribution on the right side, right? So we're going to say everything in here multiplied by square root of x first, which is square root of x times square root of x is an x. And then 1 times square root of x is 1 times the square root of x, right? And then everything in here multiplied by the 1. So that's going to be plus another 1 times the square root of x plus 1 times 1, which is 1. And I can combine like terms now. 2x plus 1 equals x plus 2 square roots of x plus 1. All right. Wow. Now I've got another equation, but there's still a square root. So I'm going to have to do this procedure over again. In fact, let me write it over here in a different color. 2x. Actually, let's do some work first. Let's isolate this term with the remaining radical first. So I'm going to do that by subtracting an x and subtracting a 1 from both sides. Subtract an x and subtract a 1. And so on this side, I'll be left with just the 2 square root of x. And over here, I'll have x, and then -1 and plus 1 cancel. So I've got, let me write it this way. 2 times the square root of x on one side equals x on the other. Okay, now, I have a term that has square root of x. Now I could divide both sides by 2 right now and really isolate the square root, but rather than introduce a fraction, what I'm going to do is, since it's all one term, I'm just going to square both sides right now. Now what is this left side? It's a 2 square root of x multiplied by another 2 square root of x. And on the right side I have x squared. So I have 2 times 2 is 4, and square root of x times square root of x is x. So now I have 4x equals x squared. Okay? This is a quadratic equation, so I need to get everything on one side and a 0 on the other. So I'll have x squared minus 4x on one side, and I'll have a 0. I did reverse those. The 0's on the other side. Now, to solve this one, we should use our factoring. Let's factor out an x. Okay, and so that means there's 2 factors multiplied that equal 0, and that means that the left factor could be 0, x equals 0, or x minus 4 could equal 0, which means x equals 4. So I've got 2 possible solutions here. X is 0 and x is 4. And how do I know whether they work? Well, I'm going to have to plug them in. So let me actually scroll up on the screen here. I've got another copy of the equation written here. And I'm just going to remind myself what it is, and I'm going to check these 2 values here. So let's check. Let's actually use a different color. So we're checking now to see whether those values work. Let's check x equals 0. Okay, to do that, I'm going to take 2 and then I'm going to plug 0 in. I'm using this equation down here as a guide. I'm plugging 0 in wherever there's an x, minus, and I'll put a 0 in there, and I'm seeing whether that's equal to 1. So 0 times 2 is 0 plus 1 is 1. So that's square root of 1 minus square root of 0 is 0. So that's 1 minus 0. So that's 1 equals 1. So that one worked, and that means this one is a solution, right? X equals 0. Let's check x equals 4. Okay, checking that. 2 times 4 plus 1 minus the square root of 4, substituting x in there as well, 4 in for that x. And so I've got square root of 9 minus square root of 4 is 2. And that's 3 minus 2 equals 1. So that one also works. So both of those solutions are actual solutions. Very good. Okay, a lot of work, right? But if you're precise and you're careful, you should be able to get the correct answers. Let's see if I've got another example. I think I just have one more here to show you. And again, you can try this on your own. Isolate the most complicated piece. I think this is the last one. Yeah, let's try this last one. So isolate this first, pause it, go all the way through, including checking your answers, see whether you have it right by unpausing. Okay, first step would be to subtract a square root of x and add a 2 to both sides so that I can isolate the piece with the most complicated square root. I'd have negative square root of x plus 2 over here. Then you could square both sides, the entire left side and the entire right side. And on the left side, the square root and the square inverse functions, so they cancel each other's effects. And then I have a negative square root of x plus a 2 times another negative square root of x plus a 2. I have to do distribution, which means everything on the right times negative square root of x. That's going to be negative times negative is a positive, and that's going to be an x. Then I have negative 2 square root of x, and then everything in here times this. 2 is going to be another negative 2 square root of x plus a 4. Combining like terms, 4 square roots of x plus 4. And let me do some rearranging here now to try to isolate this term on one side. Actually, I'm going to move that to the other side by adding 4x, 4 square root of x. So what do I have there? I have 4 square root of x plus 2x minus 1 equals x plus 4. And now I'm going to subtract 2x and add 1 to both sides to get 4 square root of x equals negative x plus 1. No, plus 5. Plus 5. Okay, let me bring that equation over here. 4 square root of x equals negative x plus 5. Now, I'm going to square both sides again to get rid of that last square root. On this side, I have 16 times x. And on this side, I have a negative x plus 1 times another negative x plus 1. And that's going to be a positive x squared minus 5x minus another 5x plus 25. When you combine like terms, you'll get this. And then, again, a quadratic, so I need to get everything on one side and a 0 on the other. And so I would have 0 over here equals x squared minus 26x plus 25. And that could be solved by factoring. So let's see, we would have negative 1 and negative 25 to give me two numbers that multiply to positive 25 but add to negative 26. And so the possible solutions are x is 1 and x is 25. And again, we need to double check those to see if they're both actually solutions. Let me bring that up here. Here's the equation again for checking. So let's see, we've got 2 times, let's try the 1 first. Minus 1, and then plus the square root of the 1, and then minus 2. And we're trying to show whether that's equal to 0. Okay, what is that? That's going to be square root of 2 minus 1 is 1, plus 1 minus 2. So that's going to be 1 plus 1 minus 2. And sure enough, that is true, and that means this one is a solution. X equals 1 is a solution. Okay, let's try one more. Let me switch colors here. So for this one, and let me do it over here. I have square root of 2 times 25 minus 1 plus the square root of 25 minus 2 equals 0. So that's going to be 50 minus 1 is the square root of 49 plus 5 minus 2. 7 plus 5 minus 2 is 12 minus 2 is 10 equals 2. And that's not a solution. So this one is not a solution. 25 is not a solution. Okay, a quick summary here. I realize it's a lot of work, but as you practice, you'll get better and more proficient. To solve equations with radicals, you should isolate the